This is question 46 from the GATE 2018 EC paper, where we are given that the D flip-flop is positive edge trigger and that D in and clock both have the same periods. The XOR gate output swings between 3.3 and 0, and that the clock has a duty cycle of 15%. We are given that the probability of D in is 0.3, and we are asked to find the average value of the voltage at node X, that is the output of the XOR gate. Underneath the question, you will find the titles of 2 NPTEL videos that are relevant to this topic.
So let us proceed to solving this problem. We are given that the output of the XOR gate swings between 0 volt and 3.3 volt, right? The output of the XOR 0 volt is for logic 0 and 3.3 is for logic high. So the output of the XOR gate will be 3.3 volts if the inputs are different. That is, if you get D in here and D in bar here, and they'll be the same if the inputs are the same, right? So let's say that within this clock edge, right, within this clock period, we find that D in has a transition. What you'll notice is as soon as the clock goes high, right, whatever is D in will get sampled and gets passed along here. So after the clock goes high, X will be 0. And until D in changes within that clock cycle, X will remain 0. Right? Until D in, that is this input, becomes D in bar within this clock cycle, X will be 0. So we have presumed that within this clock cycle, D in is going to flip at this point. So for 0.15 T clock, the output X will be 0, because the inputs to the XOR gate are both the same. Now as soon as D in flips, right, that is D in becomes D in bar, it will take until the next clock edge for D in bar to come here, right? So for the remainder of this clock period, the inputs are different to that XOR gate, and so you get this as the waveform. But remember, D in bar switching is not a guaranteed event. So we are given that the probability of the data bit to transition in each clock period is 0.3. That is 30% of the time it's going to be like this, but 70% of the time it's going to be like this, right? That there is no transition here, and so D in the inputs to the XOR gate are both equal. Anyway, they're going to become equal after the passage. They just continue to stay equal after the delta T point for the remainder of the clock period, right? So 70%, so this is what it's going to look like 70% of the time, and this is what it's going to look like 30% of the time. So now we can get an average voltage as follows. That is the average voltage at the output X. So the idea is that this is going to 3.3 volt and this is 0 volt. So the average voltage is, that is the expected value of the voltage is probability that D has a transition and probability that D does not have a transition, right? The probability that if D has a transition, right, then for how long the voltage will be high within that clock period, right? So if D has a transition within the clock period, it's going to be high for only 0.85 of the clock period, right? So if this whole thing is 1, it's going to be high for 0.85. So we multiply this by 0.85, and the voltage that it is at is 3.3 volt. Of course, it's only going to have a transition 0.3, that is 30% of the time. And of course, probability that D is equal to 0 times the average voltage for when D is equal to 0. So when D does not have a transition, that is D equal to 0 means D does not have a transition. So when D does not have a transition, the voltage is 0 throughout, as you can see here. And so it's 0.7 into 0. So this works out to be 0.8415, and rounding off to 2 decimal places, it's 0.85.